Alright, so now we're going to use our what we know about areas to try to find volumes. So, say we wanted to go ahead and look at the volume of a rectangle. So this would normally just be length times width times height. If we wanted to find the base or the volume of a circular cylinder, what we'd do is we would find the area of the base times the height. In this case, the base is going to have an area of pi r squared. So that means our volume would be equal to pi r squared times the height. Now, say we had a cylinder that didn't have a circular base, but it had two planes, B1 and B2. Here, the planes B1 and B2 form our bases. And here, if we want to find the area here of the cylinder, we want to find all points on the line segments perpendicular to B1 that join B1 to B2. So it'd be nice if we could find all these different ways of connecting these two bases and be able to kind of measure those areas. In our previous sections, we looked at estimating the area under functions using rectangles, since we know how to find the area of a rectangle. Here we're going to use kind of a similar idea. We know how to find the volume for a cylinder. So for some solid that isn't a cylinder, we're first going to cut the solid into pieces and approximate each piece using some sort of cylinder we know how to find the volume of. Then we're going to estimate the volume of our solid by adding the volumes of the cylinders together. And the more cylinders we use, similar to how the more rectangles we used for areas, the closer we're going to get to the exact volume of the solid. Alright, so say we want to go ahead and estimate our volume. Well, how we're going to do that is we're going to intersect the solid S with a plane to obtain a plane region that is called a cross-section of S. So we kind of think of taking our solid S that we have down here and kind of slicing it up with a knife at some value of X. We're then going to let A of X be the area of that cross section of S in this plane P, P sub I, perpendicular to the x-axis and passing through the point X, where X is somewhere between our A and B that we have as our endpoints. So something to notice is that the cross-sectional area changes depending on X. In other words, depending on where you slice. So what we need to do is we need to figure out what these different cross-sectional areas are. So we need to find our cross-sectional areas, A sub X. A of x. Once we do that, we can try to figure out how we make these cylinders. So say we've got this area we found here. If we wanted to go ahead and use those areas, similar to how we had with our rectangles, what we can do is we can choose one of our areas and then choose some sort of width to create a cylinder. Basically, that would be kind of thought of as the height of the cylinder. And this divides us into slabs or slices for our solid. Now from here, we're going to choose some sample value x from each slab and use its area to kind of give us the height of each of those, or the other dimension that we need. So here we've got x of I sub I minus 1, x sub I star, and x sub I. Then the x sub I stars in this picture are the centers of where we sliced. And so these are what we're using as kind of our different heights for each of these. So the volume of each slice here will be estimated by treating the slice as a cylinder. So the volume of the ith slice, so S sub I, will equal the change in x times the area of x sub I star. So in other words, we can think of this being our height and this as being the area of the cross section. And so then that would mean that the total volume would be found by taking and summing up from I equals 1 to n, however many we decide to have of these little slices of A of x sub I star times delta x. In other words, we're going to just add up all the volumes of those slices. Well, wait a minute. When we were trying to do that with our Riemann sums, what we found is that if we wanted to just go ahead and, take more of these rectangles, or in this case slices, we should get a more accurate picture as far as what the area, or in this case volume, is going to be. And in fact, if we take an infinite amount of them, then by taking an infinite amount of them, we should be able to get the exact area, or in this case, volume. So here's our definition for volume. Let S be a solid that lies between x equals A and x equals B. If the cross-sectional area of S in the plane sub x through x and perpendicular to the x-axis is A sub S, where A is a continuous function, then the volume of S is going to be equal to the limit as n goes to infinity of the sum from I equals 1 to n of A sub xi star times delta x. But remember, delta x is going to depend on n. And so at the end of the day, this ends up just being the integral from A to B of A of x dx. So that was a lot of words to say. If we can find a formula for the area that depends on what the x value is, and we know what our lower bound and upper bound are, in other words, we know what we're integrating over as we go through this, then we can just take the integral from A to B of that area to find our volume.
So that sounds really easy. The hard part here is going to be making sure we have the area formula correct. So let's look at an example. Say we wanted to show that the volume of a sphere with a radius of r was 4/3 pi r cubed. So let's talk about what that means. Say that this is our circle here. Maybe this is r, this is r, this is negative r, this is negative r. Well, this wouldn't be r. This would be r over 2. This is r. And we wanted to go ahead and find the volume of this sphere. So that right now we're only really seeing part of the volume. We actually would have more to go. So say that we've got our radius along our sphere. We'll have some sort of x and some sort of y that we have to worry about. So we've got the y part here. This would be x. And what we're doing is we're trying to find our cross-sectional area of this sphere by essentially, at that individual x value, figuring out what this circle is going to look like. So this red thing in red here is the cross-section at x. So we've got a sphere centered at the origin. And we're doing that right now for purposes of convenience. The cross sections here are circles. So that's great. We know how to find the formula for the area of the circle. So each cross section has a radius of y, which we then would need to figure out what that is in terms of x. So the cross sections have a radius of y. But if we want to find that in terms of x, well, right now what we've got is a right triangle. So we can solve for y. So if we've got x squared plus y squared equals r squared, then what we end up getting when we do a little bit of algebraic manipulation is that y is going to equal the square root of r squared minus x squared. And our area for these cross sections is going to just be equal to pi times y squared. But if we want it in terms of x, it'll be pi times r squared minus x squared. Now you might be wondering, where did the square root go? Well, if we square this and we get rid of the square root, essentially we've got the square root of all of this squared, which gives us pi times r squared minus x squared. So all of this will then lead us to the ability to find our volume. So the volume is going to be the integral from negative r to r of a of x dx. Now why did I say negative r to r? Well, if that's our radius of the circle, we're only going on the x-axis from negative r to r. And so we just found that the area was going to be pi r squared minus pi x squared dx. Which means that when we go to take this integral, we'll end up getting pi r squared x minus pi x cubed over 3 evaluated from negative r to r. So when we do that, we'll get pi times r squared times r minus pi r cubed over 3 minus pi times r squared times negative r minus pi times negative r cubed over 3. A little bit out of room at the moment. So this is going to end up becoming pi r cubed minus pi r cubed over 3 minus negative pi r cubed plus pi r cubed over 3. So in order for us to combine these, it'll help to write this as 3 over 3 times pi r cubed and 3 over 3 times negative pi r cubed. So if we take 3 pi r cubed and subtract 1 pi r cubed, that will be equal to 2 pi r cubed over 3 minus, and over here when we do the same thing, it'll be negative 3 over 3 pi r cubed plus 1 over 3 pi r cubed, and we'll get negative 2 pi r cubed over 3. Negative times negative will give us a positive, so we'll get 2 pi r cubed over 3 plus 2 pi r cubed over 3, and that will give us 4/3 pi r cubed. So we don't know what the radius is, but whatever it is, we could find the volume for it by plugging into our formula for the volume. So the hardest part here wasn't the integration, I hope, because we've been practicing with integration, we've seen it a few times. The hard part here is going to be figuring out what your cross-sectional area is. Now, a lot of the times we are going to be interested in problems where we are rotating some sort of function around an axis between 2 points. So say we wanted to look at example 2. Example 2 wants us to find the volume of the solid obtained by rotating around the x-axis the region under the curve y equals the square root of x from 0 to 1. So here's what we have. We have some sort of limits here going from 0 to 1 on the x-axis. We know we have the function y equals the square root of x. And what we're essentially doing is we are taking this function and rotating it around the x-axis. So we're basically just kind of taking it and turning it around and around and around. Now here, when we look at our circle, because what we get here are a bunch of little circles, right? Essentially, we've got this main circle here, got another circle, got another circle, and these are going to be our cross sections. And they're, because we're doing this rotation thing, they're all going to be circles. So our radius of the cross section is going to just be whatever y equals the square root of x is. So in other words, it's just going to be the square root of x, the function we were given. So this is the distance from the function to the axis of rotation. So in other words, because we didn't have any extra gap here, this has a length, this radius has a length of just the square root of x. So that means the area of the cross section is going to be pi times the square root of x squared, or just pi x. That means our volume will be found by taking the integral from 0 to 1 of pi x dx. Taking that integral, we'll get pi x squared over 2 evaluated from 0 to 1, which will give us pi times 1 squared over 2 plus pi times 0 squared over 2, minus pi times 0 squared over 2. Ends up being 0, so it's not going to be that big of a deal. And that'll give us pi over 2 as the volume of this region. So if we took this and we wanted to rotate around, we'll have a volume of pi over 2. Now we don't have to just focus on looking at rotating about the x-axis. We also can rotate about the y-axis, and here y would end up being our variable. So say we wanted to find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the x-axis. Okay, so, about the y-axis. So here's x equals 0 right here. So x equals 0 is this dotted line right here. Here we have y equals 8. And if we're trying to bound that with y equals x cubed is going to look something like this. Y equals x cubed. And so essentially we are going and taking and making this area here, this region, we're basically rotating around. So imagine that it's sitting on top of this pen. If I rotate it around, the shape I got within is the thing I'm trying to find the volume of. So essentially we need to take this and make a copy over on this side, and then we will go ahead and rotate. And again, we could rotate here. We've got this whole thing we're looking at, but we're rotating and just getting this as our cross-sectional area because we're rotating about the y-axis. So here we're going to slice horizontally instead to make a disk. And typically when we're rotating about the y-axis, this is what we will do. And this means that we will integrate in terms of y. So here the radius is going to be whatever the x value is. But since we want it in terms of y, and we know that y equals x cubed, this tells us that x will equal the cube root of y. So we want the cube root of y to be our radius, since we want to have everything in terms of y. This means that our area in terms of y will be pi times the cube root of y squared, which is the same as pi times y to the 1/3 squared, or just pi times y to the 2/3. Now when we go to find our volume, our low y value here is y equals 0, and our high y value is y equals 8. So our volume will be found by taking the integral from 0 to 8 of pi times y to the 2/3 dy. And so when we do this, we end up getting pi times y to the 5/3 divided by 5/3, evaluated from 0 to 8, or just 3 pi y to the 5/3 over 5, evaluated from 0 to 8, which means that we would get 3 times pi times 8 to the 5/3 over 5, minus 3 times pi times 0 to the 5/3 over 5. So that means we'll have 3 times 8 to the power of 5/3 in the numerator, so 96 pi over 5 minus 0, or just 96 pi over 5. Again, most of our volumes that we'll be dealing with are going to be volumes of rotation. So oftentimes we're going to be looking at trying to come up with some sort of area formula that involves a circle. Now, sometimes these circles are going to be a little bit more complicated to come up with. So say we wanted to go ahead and find the region enclosed by the curves y equals x and y equals x squared, rotated at the x-axis. So in other words, we want to take this area here and rotate it about the x-axis. So we would basically copy the area over here, and we will try to find the area found by taking this and this together. Now, part of the problem with trying to do this is that we no longer just have a solid shape going all the way through. However, we do have one shape where we're taking a different shape away from it. So essentially what we have here, instead of a disc of some kind, is we have a washer, which has a hole in the center. So in order to find what the area will be for the cross section, we want the area of the outer circle say we wanted to go ahead and just use the outside part and make a giant circle that was filled in all the way through, but we want to take away the middle part, so we'll subtract the area of the inner circle. So in order for us to do that, we need to find the radius for both. So the outer radius is going to be the radius that is the distance from the axis of rotation to the further function. So our radius for our outer part is going to, in this case, be x, because x is further away from the x-axis than x squared is when we're between 0 and 1. Our inner radius, on the other hand, is going to be whatever the distance from the axis of rotation to the nearer function is. And in this case, that inner radius is going to be x squared. So our area for our outer minus our area for our inner, which will help us find the actual area that we're looking for, will be pi x squared minus pi x squared, or in other words, it'll be pi x squared minus pi x to the fourth, or just pi times x squared minus x to the fourth. So if we want to go ahead and find our volume will equal the integral from 0 to 1, where these meet, of pi times x squared minus x to the fourth dx, which will give us pi times x cubed over 3 minus x to the fifth over 5, evaluated from 0 to 1, which will give us pi times 1 over 3 minus 1 over 5 minus pi times 0 minus 0, which will give us pi times 1/3 minus 1/5 minus 0, which will give us 2 pi over 15 as a final answer. Now these solids that we've looked at so far are going to all be called solids of revolution, because what we're doing is we're obtaining them by revolving some region about a line. In general, what we can do to calculate the volume of a solid of revolution is we can find the volume by either taking the integral from a to b of a of x dx, or by taking the integral from some different values c to d of a of y dy. Again, it really just kind of depends which variable we are trying to integrate with respect to and focus on. Now we can find this cross-sectional area a couple of different ways. If the cross-sectional area is a disk, in other words, it is solid, no holes in the middle, we'll find the radius of the disk in terms of x or y and have the area be equal to pi times the radius squared. And this was what we saw in examples 1 through 3. Now in example 4, what we saw is that the cross-section was a washer. We actually had some sort of inner radius and outer radius because we had kind of a middle portion that was missing. So what we want to do is we want to compute the area by subtracting the area from the inner disk from the area of the outer disk. And how we do this then is we get our total area by finding pi times the outer radius squared minus pi times the inner radius squared. So we've got a couple of different ways to kind of look at finding these disks and washers and finding what those cross-sectional areas are. Now, what you might have noticed at this point is that I keep saying that we're rotating or revolving around a line or a axis of rotation. I'm going to kind of underline that real quick. Well, the truth of the matter is we don't always have to just go around the x-axis or the y-axis. What we could do instead is we could pick some line that we wanted to rotate around. So for example, say we wanted to find the volume of the solid obtained by rotating the region from example 4 about the line y equals 2. So we're going to have the exact same region as before. So we've got, I'm going to draw this a little bit differently than I had anticipated. Here's 1. Here's 1. There's y equal x. There's y equals x squared. And now we want to rotate it around the line y equals 2. So here's y equals 2. Here's 3. Here's 4. So what now we're doing is we're taking this region and we are having another copy up here, and we are taking this solid and we want to rotate this region around the line y equals 2. Should go to there. And so now these are going to be our washers, our cross-sectional areas. So the question is, how do we find these distances? And of course, we are doing a rotation. Make sure it's clear that that's a 2. So this is going to be our washer method, our washer way of doing things. Our in will be the distance from the axis of rotation to the closest function. Now in this case, the function that is the closest is x. So if we want to know how far apart these are, we're going to take x minus 2. And if we want to find our outer radius, this will be found by taking x squared minus 2. And so that means that our area, in terms of x, will be equal to pi times x squared minus 2 squared minus pi times x minus 2 squared. So if we want to find our volume will be found by taking the integral from 0 to 1 of pi times x squared minus 2 squared minus pi times x minus 2 squared dx. And I'm mostly looking on the scanned homework to see if you can set these up. So you've got your outer radius, you've got your inner radius. And so when we go ahead and go through this process, you'd want to FOIL these out before you integrated. But what you should get if you want the extra practice with integration is 8 pi over 15. All right, we'll do one more example. Let's say we wanted to find the volume of the solid obtained by rotating the region from example 4 around the line x equals -1. So notice that before we had a horizontal line. It said y equals 2, but that meant that it was horizontal. So because of that, we're still rotating with respect to x. Now, because we are rotating about a vertical line, we'll actually be rotating with respect to y instead. So here is the normal x and y axis. Here is our 0 to 1 that we're used to dealing with. And now we've got the line y equals -1. So y equals -1 that we'd like to rotate this region around. So we'll be taking, we have some sort of inner circle and some sort of outer circle, and we are hoping to find these areas. So now, because we are rotating, so if we want to rotate around a vertical line, then we will integrate with respect to y. So let's say we wanted to go ahead and find our inner radius. Here, the closer function to this is going to be our y equals x. So if it's y equals x, well then we know that y equals x. So normally we would want to figure this out based on what these distances are in x, but in this case we end up getting that the inner radius is going to be y minus -1, or in other words it'll be y plus 1. So basically we have this extra distance here that we're adding to it. So normally it's y if it was just the y-axis, but now we need to add 1 to make that distance a little bit further. When we look at the outer radius, because y equals x squared, this tells us that x equals the square root of y, so this will be the square root of y minus -1, or in other words, it'll be the square root of y plus 1. So that means our volume will be found by taking the integral from 0 to 1, because that's what we still have our bounds for y as, of pi times the square root of y plus 1 squared minus pi times y plus 1 squared dy. Again, if you're doing the scanned homework, I'm mostly looking to see if you can set these up. But if you wanted to do the integration or get a little bit of practice for the WebAssign, this will end up giving you a volume of pi over 2.
Now this is not the only way to try to find volumes. There's another method that we'll end up exploring in our next video.